Good. Hey, everybody. Welcome to Data Science Learning Community. We're reading the book, The Effect. Uh, I believe this is our last official session, covering the second half of Chapter 21, Gallery of Rogues, and Chapter 22, Under the Rug. So these are both miscellaneous chapters. Um, did you folks have a chance to get through all these? I know some weeks are tougher than others. Um, I just finished early this morning, so I am certainly not an expert in all of this stuff, but I think I got enough to at least get through discussion here. Um, so we'll start with heterogeneous effects. Right, this is a common problem. Heterogeneity has been discussed, I think, briefly in other areas where like the effects of treatment are not necessarily constant across all observations. But some of these models we look at just focus on mean effects and don't really break down that heterogeneity into components. And there are ways you can go about modeling the heterogeneity. The simplest way you could go about this, if you don't have too many variables in your model, like if you're working with a linear regression, you could just include interaction terms, right? So that you have different predictors that you could interact with your treatment variable, for instance, and that way you could get a um, this heterogeneous treatment effect that you're looking for. Um, there's also hierarchical models like random and mixed effects type models that allow for um, dealing with heterogeneity, particularly when there's a kind of, well, as the name would imply, a hierarchy, right, of relationships between variables. Like a canonical example would be like school districts. You have schools within those school districts, and then classrooms. So those types of models work well with that. Um, and then tons of machine learning models. The big ones I'm familiar with would be like random forests and XGBoost type models that have decision trees being formed under the hood, and those models are pretty good at capturing interaction effects that you don't have to specify directly when you're formulating the model. So those can capture some of those heterogeneous effects. And the author talks through a couple examples. Uh, here's a machine learning approach. I hadn't heard of this before, causal forests, which really is just a modification of a random forest. Have you guys used random forest at all for any of your work? Ashley raising her hand. Yeah, so that's kind of a Swiss Army knife tool um, for folks that are doing machine learning. It's one of those algorithms that doesn't require a lot of feature engineering. It tends to have pretty decent predictions with minimal tuning. Again, it's a decision trees under the hood. And in the book, they kind of go through how a decision tree works. So, you start with your sample of data. It looks at each predictor one at a time and figures out the optimal um, predictor to do a split on. And usually there's some sort of impurity measure, or that could be something like mean squared error. So it's a greedy algorithm, and it splits things in two. Like if we have age, it will choose a random age. You could think of age as somewhat continuous. I guess technically it's discrete, but I think you get the picture. A decision tree would split things out into discrete buckets. In this example that I took from the book, they're splitting at 64 and below, and then 65 plus. And a decision tree might actually split ages at various points in the tree. It's just at each decision node, it kind of has to make a choice. And so there's a lot of artistic choices you can make with these decision trees. But they are super useful, although they tend to overfit data from a prediction standpoint. So back in the late 90s or early 2000s, the random forest was created. And so that really, it uses what's called a bagging method, where you're basically averaging out the results of many decision trees together. So decision trees tend to have low bias, high variance, but random forests kind of help with the variance issue. So it's less likely to overfit. And the key change with a causal forest, instead of splitting on an impurity metric, it splits based on how different a treatment effect is. So hopefully I didn't read this incorrectly. Again, I a lot of material and I read it through briskly, but my understanding was that the split's made based on where the bigger effects are. So it's trying to split to say like low effect here, high effect there. There's a big difference. So if you're looking at if you have retirees and non-retirees, a lot of folks, at least in the US, retire at age 65. You might expect to see a bigger effect starting at age 65. And this causal forest algorithm might find that naturally without having like an explicit like retiree label.
So it can help if you don't have too much domain knowledge, kind of?
Yes, so that's a good point. Certainly in terms of the overall formulation of the model, you don't know exactly which variables to include. You don't know about interactions, higher degree, like polynomial type stuff. Random forest or causal forest can handle some of that for you. I will say, just from a practical standpoint, using random forests, like sometimes you still want to specify interaction effects if you know it to help it along. But yeah, it can find some of these on its own. So you're right. Like this can be very helpful if you don't have full domain knowledge.
Oh, cool.
I mean, it kind of selects variables, right? Important variables for you. There was an example in the book about cutting cable, right? Standard kind of cable, and just going on a streaming package and estimating the effect of TV watching there. But I'm not going to go into the details of that. There is an R package, GRF, if you're interested. And with any sort of like collection of decision trees using a bagging method, it comes with standard errors. Like that's kind of one of the byproducts, which is nice, not just kind of one estimate. The standard errors kind of come for free of what you're measuring. All right, moving on, sorted effects. This one I had to read through a couple times. The author talks about this as being kind of obvious, at least the initial structure, but you could think of, I don't know, having just a basic linear regression where we are modeling the heterogeneity through a bunch of interactions, right? The interaction of your treatment variable with a handful of these other variables that you're interested in. And then you can essentially get a treatment effect for every observation. If your treatment is like a 0 or 1 binary variable, right, you can get a prediction assuming that is 0 or 1, but leaving all the other coefficients the same, right? So that kind of gives you a treatment effect right there. And you could do that with every observation in the data. So you have observation level treatment effects there. And so that seems pretty obvious. You could do that with a lot of these models we've talked about. One thing you do with sorted effects is you literally do sort the effects, though, which is what we're trying to show you in this graph from the book here. Just how the effects vary from individual to individual, and here we have some confidence intervals around it. There is some complexities that happen under the hood. Details are limited, but there is a bootstrapping that goes on there that you don't get out of the box with like a typical like OLS type model to estimate the standard errors of each of these individual effects. And trying to estimate effects at the tails of the distribution is always hard for most models. And there's some other features of this approach that do a good job apparently of handling that noise. So again, this is more of a whet your appetite kind of thing as opposed to a deep, how does this work? But here's a cool thing you could do using this kind of approach is you could actually here bucket your effects into like people that weren't very affected and people that were the most affected. So bottom 10th percentile and top 10th percentile. And this particular exhibit is referencing a study where it was the effect of recommending vitamin E on vitamin E usage. And I think the author of this study had this hypothesis that really the folks that took vitamin E were already healthy to begin with. So it's not like vitamin E made them more healthy. And just an interesting thing about this graph is you can see that the folks that weren't as affected by the recommendation were 100% of them were smokers, and 100% of the most affected weren't. And then there were these exercise rating scores as well. I think they were kind of standardized. Think of like a Z-score or something like that. And the folks that weren't as influenced by the recommendations didn't exercise as much, and the folks that were affected did exercise a lot. And surprise, surprise, the folks that were affected already tended to take vitamins. So I thought that was just kind of an interesting example here. If you're interested in this approach, there's a sorted effects package in R. All right, and so last piece of chapter 21, and Sarah, I'm curious if you're familiar with the structural estimation approach. Apparently, it's like a subset of economics that really goes deep into this. I was a little
I think it
confused.
exists, but I've
Yeah,
never seen it in action.
yeah, yeah. So I was initially confused in this section. I had to read it a couple times. There's a footnote to say like, hey, don't be confused with structural equation models, SEM, which is used for causal inference, although he was saying that's kind of related. Really what he's getting at is letting theory truly influence how you're creating your model. So it's really a model of how the world works as opposed to these empirical inference models that we all tend to rely on, like linear regression. We know in the real world, a lot of times your processes are not linear in nature. They tend to be useful, but aren't really modeling reality. There's a lot of discussion about this, by the way, in the book Statistical Rethinking. I think I've mentioned that book in the past. It's a Bayesian inference book, but it also goes into causal inference a lot. And the author of that book talks about how, regression in general, like, yeah, it's a useful tool, but it's not modeling reality in a lot of times. And there's discussion about like planetary motion, and there's great models to predict where planets are going to be at various points in the year in the sky. But like these early models were good predictive models, but they didn't actually, they really got wrong how planetary movement worked. And so in more modern times, folks figured that out, that we're both predictive and actually got the model right. And so the author talks about, this classic equation from physics about force between two masses, right? And it's has to do with how far apart they are and the masses of each object. And he had a point that if you actually are able, if theory gives you a good model, you should use it because you're going to end up with a cleaner causal model. You know what I mean? You've clearly identified reality. The issue is when you create these models, they tend to be a lot less tractable from a mathematical perspective. They're not as easy as like a linear regression. So they are difficult to work with, at least from what I understand in the field of economics for the folks that are using this stuff. Oh, okay, so that was chapter 21. Now there are quite a few different pieces in the chapter 22, which is entitled Under the Rug. This chapter is about just, hey, these are things that we didn't really talk about much before, just notes of caution, right? There's a lot that can go wrong with the approaches that we use. And so this chapter doesn't talk about the method so much as just like things to be aware of when you're doing research design or when you're fitting models. And so, we kind of consider this to be a survey chapter. So again, kind of broad, pretty shallow, but just exposing us to some of these topics. The first of which is model uncertainty. And when we talk about uncertainty in our models, we typically focus on the sampling variation. If you're talking a linear regression model, we tend to focus on that error term or maybe the uncertainty in your coefficients. But we oftentimes we fail to think about additional sources of uncertainty, which is like, well, was my model right to begin with? And so we could think about multiple statistical models, which one is the most appropriate. The most common approach is just to pick a model based on predictive performance, even when we're talking causal in the causal inference world, right? If it's an OLS, you could think of like R squared or something as, or AIC or some other measure kind of guiding you as to what model makes the most sense. So that's pretty common in terms of research. Another thing you see out in the wild is folks might use a few models, particularly if they're not 100% certain on what the right model is, report on the results for each of these models. And the idea is if you're getting roughly the same treatment effect, if that's what you're interested in here, across these models, we would say that our result is robust, right? We're getting a statistically significant result, same direction, maybe rough, order of magnitude is the same across different models, which is a good thing. But the author talks about, well, that's kind of an ad hoc approach. One other thing we could do, which is more common today, is fit a ton of models. And when we talk about models, we could mean different model types, right? You could have an OLS model, like a random forest, an XGBoost model. But the example he gives here are just basically the same underlying architecture, like an OLS type model, but like some models include certain variables and exclude others. And maybe we don't know, maybe we know there's a set of variables W1 that should be included in your model, but then there's another set, W2, that we're not sure about. So if there aren't a ton of these uncertain variables, you could just run every single combination with and without. Or there are other algorithms out there that you could kind of sample from, these combinations. If you have a lot of variables, this grows so quickly that it just becomes unfeasible to test every single possible combination. But let's say you end up with hundreds of models. You could report the mean effect across all of these models together. And then you get like a variation across the models as well. So you have, kind of a standard error and mean based on using all these different models. And then as an extra layer of complexity, instead of just taking, a arithmetic average of all these models together, you could do what's called Bayesian model averaging, which is just, I guess, a cleverer way to apply weights to your individual models. You have a prior estimate of which models are better than others. Could be based on subjective insights or prior research. And then, of course, in a Bayesian approach, right, you actually look at the data and say, well, this model actually does fit the data better. So combining the prior with the data, you get like a posterior weight. Okay, yeah, Ashley, you're saying seen weighted averages based on AIC. That's interesting. Yeah. And I'll just say, just with some of the machine learning work that I've done, there's an ensemble modeling approach that often happens. So you might have a lot of complex, kind of nonlinear machine learning models, and then there's a couple approaches called like stacking and blending, where you just have like a final meta model, which could be an OLS model, where you take the predictions from your base learners, right? And you let the OLS choose kind of your weights for the different models that you're averaging together. And there's some clever complexities with that as well, like, test data and holdout data and all that stuff, so you're not overfitting. But that's the basic idea I'm familiar with, at least in machine learning. Okay, next section. Again, like I said, lots of topics here. This is about measurement and validity. oftentimes we're handled data sets, but we don't really think about how the data was generated, and data is never perfect. A lot of data is generated from humans, and we're fallible beings, right? Um, a lot of research is done based on survey data, and framing of questions and how respondents interpreted questions are very important there. And another issue is that most surveys don't look at a representative sample of the population that you're interested in. So if a survey is designed well, it will come with survey weights that you can apply to the actual data so that you get something that looks more like the when applied, you get something that is approaching the population of interest. And then there's this, measurement error in general. Like the example in the chapter was some respondents just aren't good at actually accurately telling you what their educational attainment is. Maybe they just, if it's like, how many years of education did you have? I don't know. If it's been a while, you might not remember exactly. So that I thought that was a kind of a funny example. So then we have construct validity, which I misspelled, which I will clean up hopefully before this final version goes to the Git repository. But yeah, so the idea here is how well does the data actually measure what we're trying to measure? And the example in this section is trust, right? And that could be like trust of government. You might ask a respondent to measure their trust of government on a 1 to 10 scale, but do respondents really understand what that means? Like, how different is a 9 from a 5, for instance? Different people could interpret that different ways. The word trust itself is kind of ambiguous, right? Like your version of trust may be different than my version of trust. And even if we all have a universal understanding of what trust is, how good are we at actually reporting our levels of trust? Maybe it's not something we've really thought about that much, and in the moment we just kind of throw something out there.
And then on top of that, there's also a reversion to the mean, right? That people tend to not give ones and tens. And I think like most are like sevens or eights.
Yeah, that's a good point. Unless you're doing like a review of a product, right? And then it's usually the extremes. You only
Yeah.
feel compelled if you really hated something or you really love something.
Yeah.
And then you have something called the Linda problem. I think this is just one example of how construct validity can be called into question. And the idea with this one is folks are given a story about this woman named Linda, and they give details about her background that are supposed to give you the impression that she is a feminist, right? And so after that vignette is discussed, a question is posed. Is Linda more likely to be a bank teller or a bank teller and a feminist? And more people respond by saying she's more likely to be a bank teller and a feminist. But that's impossible, right? If you just think about the laws of probability, the probability of being a bank teller has to be greater than or equal to the probability of being a bank teller and a feminist. Just how probability works. So it's just people are not 100% logical. I think it's kind of the deal with that. So be careful. And it's just an interesting, useful example to think through. Another problem is like, maybe you need income in your model, and you have wage data potentially from your government, right? Like IRS tax returns in the US. And there's a question of, well, there's different types of income. Is it pre-tax income? Is it just your wage income, or would you include investment income? Again, it could be pre or post-tax. And these choices may actually influence what treatment effect you're trying to measure. So these are not necessarily trivial questions. There's a whole field called psychometrics. It was just mentioned briefly here, and a lot of literature on content validity. Reliability theory is a I have a book on that I haven't read. I mean, to just this comes into question a lot with tests, right? Like you're measuring someone's IQ, like how reliable is that? Like, or if you have someone take the same test today, do they tend to get the same results when they take the test the next day? Um, yeah, just lots of research on that we can't really discuss in our last 25 minutes here, but it was commented on in this section. Okay. There's the observer effect, which I think most of us have probably heard of at one point in time. This comes into play in particular when you're dealing with people, when you're measuring things people do. If you're an economist or a sociologist or any sort of social science field, when folks know they're being observed, their behavior changes. Sometimes because they want to behave in a way that the researcher expects. Maybe they want to impress the researcher. Maybe they don't like the researcher and they're trying to, I don't know, spoil what the researcher is trying to do. But nevertheless, just the fact that people are being observed, they know it, their behavior may not occur in a natural way. Um, and that's something you want to think about as you're designing your research. Happens with animal behavior too. Yeah, actually, good good call out. Right. I mean, we're all animals, right? Social behavior. I mean, you create these artificial situations trying to measure reality, and it doesn't always work. Uh, yeah, so trying to address this after the fact is very difficult. All right. Final piece in this section is just about processing data. Um, you know, if you're dealing with a survey, you may have this issue where there are mistakes. Respondents just responded to the wrong question, or it was obvious, and you might want to correct for that. But doing so, you might be introducing your own biases. Uh, there are issues if you have free form responses, like how do you interpret those free form responses and maybe bucket those into categories? Um, Potentially based on certain responses, you could say, well, these observations don't apply to what I'm trying to do, and you drop them. But other researchers may choose to include those observations. So again, there's this bias issue that comes into play. And I believe the author himself did a study where they looked at how researchers handled the same data set, and they found that there was quite a diversity in how they handled data, how they processed them, and so that did affect treatment effects and reported standard errors. And then one more interesting thing just about kind of data issues, and this uh, is in particular affects the field of genealogy, where I guess some terms that are used in that field get represented as dates in Excel. And it apparently at one point in time, like 20 to 25% of like research was being affected by like Excel errors, where like these variables were being translated as dates in Excel, so some of the calculations were being screwed up. Um,
I did
Going
hear
back,
like a replique to this one study about like how different researchers interpret data very differently. I don't know if it's the same study about processing
mhm.
data, but apparently in that original study, they hadn't been given exact instructions on what the research question is. So I think it wasn't as much on like data processing and more on the whole stuff, like the first half of the book, thinking about what's actually going on and what you want to study.
Okay, right. Okay, so kind of the design of it just
Yeah.
varied very drastically. Yeah, there's just a lot of opportunities for interpretation, right? And yeah, it happens at the design phase. It happens at the data phase. And I'm trying to just respond to Ashley's comments here. She had to fill out a survey. Bunch of questions like, if you're reading this, select option 3. Don't think I'd seen that before. Wow. Yeah. So I guess that's a way to vet out the people that aren't really being serious with the responses, right? Um, another, I don't know if I mentioned this or not in a later section, but the chapter did speak to, like, in good surveys, you often see the same question being rephrased multiple times, essentially, just to avoid some of these interpretation difficulties. And uh, I think there are tools and techniques out there to kind of take out these multiple responses and maybe average them together in a certain way. So that way you may be getting a more robust result. Okay, next section, doing a time check here, 20 minutes. This is missing data. Something that I mean, it's a causal inference problem. It's a research problem. It's if you work with data, you deal with this issue. Um, and a lot of statistical software by default tends to just drop any observations where there are any missing values. Um, and you should be aware of that, and that may or may not be the best thing to do. And so this section just gives an overview of the different types of missing data. I was aware of most of these except for the not in universe bucket that the author describes, which is really like a not applicable designation. He gave this example of like you're studying, I don't know, business owners, and your data set includes folks where you have a field that's like number of employees. And well, if the person under observation isn't a business owner, it's not applicable, right? So that field might be missing. So in that case, it's probably okay to just get rid of that observation altogether, right? Because it's not specific to what you're trying to study. Um, However, I'm sure I've probably seen data sets that had number of employees as a field, and an observation might be relevant. You could just say a not applicable value could be 0 in that case, right? Um, so I don't know. I thought that was maybe an unusual example, but the point makes sense that, like, yeah, if the observation itself isn't relevant to what you're studying, dropping it is not going to be a big deal. The other three buckets come up in the literature all the time. There's the missing completely at random. That's the best case that you could have, but I don't know how much this actually happens in the wild. This means that really there is no pattern whatsoever to these missing values. So um, looking at maybe other covariates wouldn't really help you to predict the missing values because they're just completely unrelated, right? There's no pattern at all. And so if you have that situation, it generally um, isn't going to hurt your study if you drop those observations. Unless you already have a small sample size to begin with, right? You could have just small sample size issues, but this is the most favorable situation that you can encounter, is missing completely at random. More typical, however, are going to be the latter two cases, which are missing at random and missing not at random. And so missing at random means it is related to observed data that you have. It's not as big of an issue as missing not at random. And there's a lot of imputation procedures that we'll talk about in just a minute to help fill in those gaps. It's trickier when you have a missing not at random situation. That's where the missing value itself is related to the unobserved value. And the example given in the book is you have height and weight measures, and let's say you have quite a few missing values for weight. There could be folks that are embarrassed about their weight, whether it's too low or too high. And so because they have an extreme value, they don't want to report on it. So that would be missing not at random. And there aren't really great approaches out there. I mean, the author talks about you have to really have good theory, understanding how that missingness worked, and maybe have a model there for filling in those gaps. But it's going to be based on a lot of assumptions that may not be valid. And so the easiest thing you can do when you have a missing value is something like mean or median imputation. So, look at all of your observations. Let's say it's weight, take the average value, take the median value, just use that, right? Anywhere you have a missing value, that could result in really strange situations if you have a really short or really tall person, because we know that height and weight are correlated. So other things you might want to do, again, if you have missing at random data, is use, basically you're creating a submodel here where you're predicting the value of the missing value based on other covariates related to that individual observation, right? Having someone's height would allow you to predict weight and gender as well, right? That those would be meaningful covariates for predicting weight. And you could use a machine learning method to do that. You could use OLS. Multiple imputation is that same idea where you kind of have, like, let's say, a regression approach to filling in these missing values, but you do it multiple times with a model, and you're kind of, models are, there's uncertainty in your model, right? In terms of like the error term, the uncertainty in the coefficients, and multiple imputation uses that randomness in the generation process to generate different values, right? To fill in those gaps. And so you could specify, and there's R packages that do this. One that I'm familiar with is mice, and MICE. And you can say, I want to create 5 values, 5 basically new data sets with missing values, and in each data set's going to be slightly different. And so once you create those 5 different data sets, you would fit kind of your model for doing causal inference 5 different times, and there are approaches to combine those together, right, so that you come up with an average treatment effect, I guess, in this case. We already talked about missing not at random. It's kind of dangerous. You can use some of these imputation approaches, but it's kind of like, there's still issues here. You got to understand the data generating process. Okay, and then there are just a few other things besides multiple imputation that you can do. Not going to go into detail here. If you have categorical data, one common approach, this is used all the time in machine learning, is just to use missing as a category in itself, which can be useful. It's very easy to do. And there are 2 other methods here: the full information maximum likelihood, if you're fitting a model to data, which allows you to still use an observation even if you only have values for a subset of the covariates that you're interested in. And then there's the expectation maximization algorithm. It's used across statistics for various things, but one use case is for missing values. It's an iterative algorithm. It can also be used for filling in missing values. Their details are kind of limited in the chapter, but it's, from what I understand, it's pretty widely used. I have not used it myself for missing values, but or neither have I used this FIML approach, but certainly multiple imputation, mean and median imputation, using kind of a missing data level in my categorical variable, are all things that I've done in my day-to-day work. How about you guys? You guys used any of these other approaches, EM or FIML?
To be honest, so far I only ever dropped them, which is
Drop them.
quite common in my field. I think
Yeah.
just try to ignore that there's going to be issues.
Yeah. And again, it comes down to like, how many of these are you dealing with, right? Is it like 2% of your data, or is it like half of your data? Right? Because dropping your data can result in bias. Again, if it's not missing completely at random. But the author notes that you kind of have to weigh the pros and cons. Like, some of these other imputation procedures might actually make the problem worse. And so, yeah, you just have to kind of think about that. But if my intuition tells me, if you don't have a lot of missing values overall, it's a very small percentage of your total observations, then you're probably not going to suffer from severe bias issues. Okay, Ashley's commenting, big issue in paleontology. Fossils are notoriously incomplete. Yes. Okay. That absolutely makes sense. All right. So we're down to the 10-minute mark. We have a few more sections. I think they're all pretty quick. This one is SUTVA, I think it's how it's pronounced, the stable unit treatment value assumption. I have heard about this before, I think in some other causal inference material I've read, but basically, this is something you want, and violations to SUTVA can be a problem in your studies, and they can't necessarily be fixed. So you want your research design to think through this. And so a violation to SUTVA would be like your treatment is different across observations. And so the example given in the book would be, employee forces that are given diversity training. One treatment could be watching a 5-minute VHS cassette, like how to be respectful, and appreciate and embrace diversity. Whereas another treatment could be a full week of in-person training with a live instructor. Those are vastly different treatments, and so you wouldn't want to treat them as the same. And then the other violation that you typically see is which would go under the category of a spillover effect, where your outcome is determined by how others are treated. And so the example here would be like a classroom. If I remember correctly, it had something to do with like SATs, which is right, a college prep exam in the US. And let's say, some students had like an outside special course on SAT preparation. Well, the fact that you had a classmate that took that might actually influence other folks too. Maybe a student that was given this extra course then starts mentoring other students, right, that weren't given this extra class. And so other folks do better in the same class on the SAT exam because there's a spillover effect. And one thing you can do from a design perspective, if you think spillover effects happen here, at least for this particular example, is you could say, not necessarily look at the individual level, but maybe a classroom level. If you think the spillover only happens within a given classroom, you could say one of your covariates could be like what percentage of the students received this extra SAT preparation course. All right, so that's SUTVA. Next section about non-existent moments. Really, we're dealing with this relates to fat tail distributions. They can be hard to manage. We've talked about this a bit in the past. We think of things that are multiplicative. You think of like a logarithmic distribution, and sometimes that can be resolved just by taking the logarithm. So you stabilize variance, and maybe your models are better behaved. But there are extremely fat-tailed distributions where even taking like a logarithm doesn't really help you out. You have some extreme value parametric models out there that don't have finite means and or second moments, like variance, right? The Pareto distribution was one that was called out explicitly, and I've used the Pareto distribution in some cases. I can't remember if that distribution in particular maybe doesn't have a finite variance, but that was again one that was mentioned there as being a very fat-tailed distribution. So the problem is you end up your data tends to be quite noisy if you have these extreme value distributions, and so rather than if the logarithm isn't going to be sufficient here, you might want to, instead of looking at a mean treatment effect, you might want to look at the median. is a common workaround here. So, you know, the 50th percentile is what folks typically do because, you know, the median would be less sensitive to what's going on in the tails. Depending on what you're really trying to measure, you could do a different percentile too, right? Like a 10th percentile or a 90th percentile. But at the end of the day, the idea is if you have a super fat distribution, you're really interested in the how things impact the typical unit. This may be the way to go. Okay, and the final section I thought was pretty amusing. It's kind of like we've done all this approach so that we've done all these we have all these techniques to have comparable units, right? It's like if we're doing matching, we've adjusted for all these confounders, and we think we have, you know, a way to look at two populations where it's you have an apples to apples thing going on there, where it's like, okay, my demographics look the same across my treated and untreated population, so therefore we can measure this treatment effect. But then you have to ask yourself, well, if these observations really are comparable, then why did group A get the treatment and group B didn't? Have we really aligned these two populations correctly, right? Like, is there some lurking variable or unobserved confounder that we just don't know about? So it kind of calls into question like observational research in general. Like you never can be quite sure because we're not doing randomized experiments that we're getting what we think we're getting. And what was called out in this section was studies on twins. And so this is a popular approach for certain things because you know, you think just by looking at twins, you're controlling for a lot of potential backdoors, right? Because if you have two identical twins, they grew up in the same household, you would think, you know, obviously there's a shared genetic history there, but also you would think the environment would be very similar as well. They had shared the same parents, born in the same date, kind of getting the same opportunities. One particular study that was referenced was about, you know, looking at twins that had different educational attainment and how that impacted income. But then you have to ask yourself, like, well, why did one twin get, you know, more education than the other? You know, are those twins truly comparable? Is there another backdoor? So I I thought that was a great way to end the book, just as like, okay, we've done all this stuff, but it still might not be good enough. So there it is. That was a lot of material in a little bit of time and just scratching the surface, but I thought he threw a lot of good stuff in there.
Yeah, thanks a lot for presenting. This was a lot, but super helpful.
Yeah, but we got through it in under the hour, so I don't think we have to reconvene in a few weeks. Although, yeah, as we mentioned before that the recording got started, I'd love to do a Q&A with the author if we get a
Yeah,
chance.
that'd be amazing.
Okay.
Okay, so I'll hit stop, right? Because we're
Yes. Yes. Hit stop.